Starting. All attendees are in listen-only mode.
Hi everybody, my name is Andrew Shikyar. I lead marketing here at FIDO Alliance. I'd like to welcome you to today's FIDO webinar, Getting to Know the FIDO Specifications, featuring Rolf Lindemann. Rolf works for Knock Knock Labs as Senior Director of Products and Technology and brings more than 15 years of experience in product management, R&D, and operations from the IT security industry. In addition, Rolf's contributed to numerous FIDO specifications and is a frequent speaker at industry events. Before we get started on today's webinar, just a few housekeeping items. First of all, yes, this will be recorded and posted on our website and YouTube channels as soon as possible. Secondly, if you have questions, please type them into the question box on your GoToWebinar client, and we'll do our best to answer them during the webinar via chat message or at the end of the webinar. At the end of the webinar, after Rolf's done with his presentation, we'll select as many questions as possible for Rolf to answer. Note, however, that there are a lot of you and only one Rolf, and we may not get to all your questions, in which case we'll do our very best to answer them via follow-up email. We'll be ending the webinar at 9 a.m. Pacific, so 1 hour from now. Lastly, at the end of the webinar, you'll be presented with a short survey. We'd greatly appreciate you taking a few minutes to complete the survey, as your feedback is invaluable and will help shape our webinar program moving forward. So with that, I'm very pleased to turn the webinar over to Rolf Lindemann. Rolf?
Thanks, Andrew. So hello, everyone, and good afternoon from Europe. So this talk is about the FIDO specifications, and let's dive into that and start with some background. So look into existing authentication methods and how they are broken today to understand what we need to get better and do better to come to better authentication solutions. So I will first want to look into one very prominent attack class we have seen in the past, and this is that criminals have stolen billions of passwords. So this is an attack on server side, regardless how good your password is essentially, and how good you protect your client devices. Attackers could just go after your password on the server side, which is pretty bad because it essentially tells you that you as a user don't have control anymore. The security doesn't depend on you and your devices, it also depends on the server side. We have seen a second attack vector, which is typically called a phishing attack. This is whenever you use a bearer token, you enter it in some device, and if that device is not as trustworthy as you expect, then the password goes to some attacker. And so this is a second important class of attacks we have seen in the past. And there's even a third one, which is a more complicated one. In this case, it's an orchestrated attack to go after your PC and after your smartphone, and it attacks you even when using username password combined with some kind of SMS OTP solution, and it's called Eurograbber, as it was going after banking applications protected with username password and a second factor, the SMS OTP. Very effective those attacks, and the bad thing at this of these attacks is that these attacks are all scalable. Right? You can do that and attack one or two or different number of targets, and the cost of running that attack doesn't depend on the number of targets you are attacking. It mainly depends on the upfront cost you have to come up with some kind of exploit framework. So let's look into cloud authentication in general. And regardless whether you are using username password or something else, it's very important to understand that people have local reach only. This means whatever I do is relevant to local devices, can have a direct effect on local devices only. Whenever I want to talk to a remote server, I need some kind of helper device. Like you see in this picture, there's a person on the left-hand side, there's some interaction between this person and a local device, and then there is a remote interaction between that device and the remote server, and of course there's some additional risk analytics done on the server and the back-end side, and both the front-end signal received from the server by some device and the back-end signal from the risk analytics system together create the authentication. Now, with passwords, we have seen there's a lot of issues. right? We have seen they could be stolen from the server. They might be entered in untrusted web applications. There are too many passwords to remember, which is a convenience part of that problem here. And they are inconvenient to type on especially small devices, the mobile phones, the smartphones we are using predominantly today. Whenever you have tried to enter a complicated password with, let's say, characters and digits and special characters on a smartphone touch display, you feel the pain, you know that this is not something you want to do while, let's say, hopping on a bus, and of course not while driving, because we don't use smartphones while driving. And if you look at those attacks from a, let's say, more abstract perspective, we see that there is a large class of what we call scalable attacks. This is 1 to 4 in this diagram here. The first thing is attacking central servers to steal data for impersonation. So whenever we want to come up with a better authentication solution, we have to make sure that we don't hide secrets or don't try to hide secrets on the server side. So make sure that attackers cannot attack servers successfully and steal data for impersonation from the servers, regardless whether they attack the servers. But if they can steal the data, that's a problem for impersonation, like passwords, for example. The second, let's say, if we would add a protection line against those kinds of attacks, these attackers won't stop attacking, right? They will just focus on a different type of attack. And this second type of attack might be remotely attacking lots of user devices. So instead of focusing on servers, they will go after our devices and send us malware and try to steal the data for impersonation with that kind of malware. So installing malware or dancing pigs apps on our smartphones or PC, and we have seen those attacks already. And even if we would protect against those things, they could go after, let's say, misusing the data for impersonation. And this is a very interesting attack. So if you make sure that all your credentials are even stored in kind of smart cards, right, very secure environments, and it's just possible by malware to misuse the credential inside that secure environment because this malware has asked you for the PIN and phished the PIN in some way and can now inject that PIN into that secure element, for example. This still makes it a scalable attack, right? It's still because the devices are always on, right? We are always connected to the internet, so malware can always do bad things because the device is running. Now, and these three are mainly authentication related. Now the fourth one, even if we have a very secure authentication, there's still of a session, there's still the possibility that an attacker waits until the secure and legitimate authentication happens, but the attacker changes the transaction. Right? Instead of transferring $10,000 to John Doe, I'm now transferring $10,000 to Joe Black, right? And that now this money is gone. So that's because sometimes attackers try to misuse the authenticated session in a man in the browser or man in the app kind of attack. And we want to look after that and see whether we can find an easy way to protect against those attacks as well. Now, those four classes are scalable, and scalable again because the number of attack targets is irrelevant for the cost of running the attack. It's very easy in the internet to attack millions or hundreds of millions of people with that kind of attack. Now, the physical attacks are only possible if you have physical access to those devices. For example, it's a lost or a stolen device. And if you look into statistics, you see that approximately 3% of the devices are lost and stolen per year. Right? This is still a large number, but it's much less than the 97% of the devices which are not being lost or stolen in a single year. So physical attacks still exist, and we need other mechanisms to protect against the physical attacks. Like physical attacks to steal data for impersonation, we need additional hardware mechanisms to protect keys and so on. Or physically attacking the user devices to misuse the data for impersonation is also a different attack which could be run if you have the time and the money to create, for example, a rubber finger, and then you can use that rubber finger on that device. But what we think is that the main threat in the days of the internet is not the physical attack. It's the virtual attack. It's a scalable attack, because this scalable attack is so easy for attackers to do and to scale up to millions of victims or attack targets in the end. So in FIDO, we want to focus on scalable attacks and make sure that whenever you use FIDO, that you are at least protected against the scalable attacks. And we still allow different authenticator implementations to come up with different protection mechanisms. Now, how does FIDO work? How do we address that issue? The first thing is, remember that first diagram I showed you, that users have local reach only. So we call that device which you ought to interact with, we call that authenticator. And what the user does with that device is something is now called user verification. So user verification is a local interaction between the user and the user's authenticator. And this could be just entering a PIN into that authenticator, or it could be swiping a finger or presenting your iris or whatever, right? And we have lots of dimensions of scalability, and we'll come to that. And the second half of the authentication protocol, and this is the part where the security is mainly determined, and this is a standardized protocol between the authenticator itself and the backend server. And since you can standardize that protocol, that means that the server in the end is independent from a technology perspective from the modality, from the biometric, the iris or the fingerprint or the PIN you are using on the client side, which makes it easy for authenticator implementers to experiment and invent new user verification methods and get to better and more secure authenticator implementations without having the need to, at the same time, make sure that relying parties are upgrading to new servers or server versions. So FIDO is based on public key cryptography. So this means essentially we are using the user gesture, the interaction between the user and the authenticator, to unlock a private key, and this private key is dedicated to a specific relying party or an app of a relying party. And on the protocol side, we run a cryptographic challenge response protocol, which means essentially we are getting a random number from the server, a long random number. We are signing that random number with a private key, which is exclusively stored in the authenticator after the key has been unlocked with the user gesture, and then we return the signed response to the server. And by that, we only have to store public keys on the server side, so no secrets anymore. So there is no attack. It's not an interesting attack target for attackers, right? They cannot steal data and then use that data for impersonation, right? They could steal a bunch of public keys, but that doesn't lead to breaches there, because these public keys don't get you anywhere. Now again, I said by separating user verification from the authentication protocol, we gain a lot of scalability. And I typically think of that being two dimensions of scalability. The first is that the authenticator can implement arbitrary user verification methods. And the user verification method is exactly the thing which is relevant for the convenience aspect of authentication. So everything which is relevant to the user, right? Do I have to enter a complicated long password, or do I just swipe my finger, or enter a relatively short PIN, which I can remember, and the PIN is always the same for all relying parties and never exposed to relying parties. So this is the first dimension. The second dimension of scalability is the way I implement the authenticator. So whether I use a TPM to protect the authentication keys in the authenticator, or I use a trusted execution environment to implement the authenticator completely, entirely, or whether I use secure elements partially in authenticators, and so on. And there is a lot of different protection capabilities which is already present in existing devices, namely secure elements and trusted execution environments. So the function of the authenticator is essentially to recognize the user. So is this the same user as enrolled before? Right? When I just buy my authenticator, the authenticator is open to any user, and then I enroll my biometric or in general my user verification data to that. It could be a PIN even, right? just enroll that to my authenticator, and this binds the authenticator to me as a person. And the second kind of binding I have to do to the relying party. So whenever I sign up to a new relying party, I have to register my authenticator to that relying party. And registering that authenticator essentially means that the relying party server is now able to recognize me as a user. So is this the same authenticator as registered before? And if it's the same authenticator, I know that it's the same user as enrolled before, and then I know, yes, now it's the same user. So there's something I don't know, and this is what kind of identity does that user have? Is this a John Doe type of user, or is it Mickey Mouse or the dog, right, in the internet? And so in FIDO we say we have to do an identity binding, but since the notion of identity is region specific, it's not scalable across the internet, it's different in each jurisdiction because it ties back to the legislation in that specific region, right? From a data privacy perspective, it's one aspect, and also the expectation of the users, what they are used to expose to relying parties. And so we said, this doesn't scale on a global basis in the same way as authentication can scale and should scale. And so we separate that identity piece from the authentication piece and say, FIDO addresses authentication only. And the identity piece is what can and needs to be added by each relying party differently. And for example, banks have very strict rules on know your customer, how they have to do the identity verification, the vetting of the user. And this even depends on the region where the bank operates, right? It's different in South Africa than it is in Europe or let's say in Asia, for example. And on the other hand, it also depends on the vertical you are in. If you are running, right, you couldn't care less about the user's real identity, right? You just want to recognize the user to make sure that whatever one user uploaded, only that one user can access and can grant access to other users, right? To make sure that this legitimate user stays in control of that. There's one element more I've omitted so far, and this is attestation. Now, if we have that great scalability in terms of different user verification methods and different implementation options for the authenticator, this leads to different security characteristics of the authenticator. And that is very interesting to a relying party. So the relying party wants to know whether this authenticator is a more secure one, for example, using implementation in a trusted execution environment, or is a not so secure one using an implementation in a rich operating system, for example. And so in FIDO we decided to add attestation to that. And attestation in the first place allows an authenticator to convey the model of the authenticator to the relying party using a cryptographic proof, which is a signed attestation object. So in more practical terms, it means that the fresh key pair the authenticator generates for that specific relying party, and then the authenticator extracts a public key, and that public key, that is signed with the attestation key and the authenticator model name in it. And now the relying party needs to have some metadata, some information about authenticators, which at least includes the attestation public keys or the attestation root certificates to understand and being able to verify the attestation object. And once the server has verified the attestation object, it will then look into the same table and see more, let's say, the characteristics of that authenticator. For example, is that key in the authenticator, is it protected with a TEE or a secure element, or is it protected by a rich operating system? And what kind of user verification method does the authenticator use, and so on. So there's lots of details. And there are different ways to get to those metadata. So you could talk to each authenticator vendor individually, or you can go to a centralized location, for example, mds.fidolines.org, which is a central metadata service of the FIDO lines, and then you can download all the metadata which has been published by authenticator vendors. There's no need for authenticator vendors to publish that, but it's in their interest to publish that data. And some more words about the authenticator. So we are all used to smart cards, right? The EMV chip and pin is the latest invention in the end in smart card space, where we see a smart card which is a very secure element. And the question is, how does it relate to the FIDO authenticator? So in FIDO we have taken a lot of those elements, but we have added one more. And the thing we have added in addition to that is essentially, to be honest, two things. It's first the user verification or user presence check. So a smart card receives some kind of PIN from the user, but the PIN is entered into a secure PIN pad in a card terminal or not so secure PIN entry dialog box running by some dancing pigs application, right? And the smart card itself can't tell the difference between those. In FIDO, just by definition, we specify that the user verification piece, so the fingerprint sensor or the PIN entry dialog, including the PIN pad, is part, by definition, of the authenticator. And the second thing we have changed as well is we have added a thing called transaction confirmation display to make sure that the purpose of the authentication, of signing something, the random challenge, can be added to that signature. And this can be displayed to the user, and there are different ways to implement that transaction confirmation display. We will come to that. In addition to those optional components, there are other components, for example, the attestation key, which is typically injected at manufacturing time, and there's no need to change the attestation key during the lifespan of the authenticator. And the second is a bunch of authentication keys, and those authentication keys is one per relying party. In the end, they are stored inside the authenticator, and that grows over time the more you register the authenticator to different relying parties. And those authentication key pairs are generated by the authenticator itself. There are different ways to implement that authenticator. So first, you can use a smartphone and have the authenticator built into that smartphone. The second could be an external device, like a USB a token with, let's say, at least a button on it for user presence check. And we have seen those as well, and they add a lot of security. And when it comes to authenticators which are built into smartphones, they are typically based on trusted applications, or they are implemented in a trusted execution environment, and then it's called a trusted application. And this is a typical architecture you see there. And you see additional characteristics of FIDO concept, which is that the user verification data, think of this as being the fingerprint or the PIN number, so the biometric data or the PIN, is not visible outside the authenticator, and there's no need to expose this very sensitive data outside the authenticator. So instead, it stays inside, it's compared inside against the templates or the reference data in general. And once this comparison has been done and is succeeded, it will unlock the key, and then the cryptographic engine of the authenticator will perform the signature of the random number. Right? So everything stays inside the authenticator, all privacy relevant data and all from a security perspective relevant data, which makes it easier to protect this data. Now, you might have heard that in FIDO we have different protocol families, and one is called passwordless experience, the U2F standard, and the second is called second factor experience, the U2F standard. And everything I've told you so far is similar for both, right? The standards only have differences in, let's say, smaller encoding details. But from a security perspective, they're pretty similar. Let's start with U2F, the universal second factor experience. So as the name indicates, it's a second factor, which means the relying party also needs the first factor being used before that second factor can be used, which also implies that the relying party already knows the user. So now assume you want to register your authenticator, your U2F authenticator to a relying party. So you have to enter username password, which you typically already have, and then you say, now I have a new A U2F authenticator might be a USB token. You insert that to your device, and then the relying party sends you essentially an app ID or the name of the relying party. Think of this as being the google.com thing, right? And a challenge, which is a random number. Then the browser checks that the TLS certificate also says google.com, and the app ID matches that thing and sends over some data which we call the final channel, which is denoted as FC in this diagram, which is a concatenation of the app ID, the challenge, and the origin, which is a login.google.com or things like that, channel ID information of the TLS channel, and etc. And then it computes a hash of that, and that thing is sent to the authenticator. And the authenticator will then generate a fresh public key, generate a key handle, and spit out a public key, the key handle, the attestation certificate, and most importantly, the attestation signature, which is a signature over the app ID, the final challenge, the public key itself, and the key handle. And that thing is then sent over to the relying party. The relying party returns or has as a cookie after the password authentication, and then knows, oh yes, this is the John Doe wanting to register a U2F authenticator, and I store the public key and the key handle. And the next time John Doe comes up and wants to log in with username and password first, I will then respond with the key handle I've remembered for John Doe with the same app ID and a new challenge, send it out, and that again goes to the authenticator, which then doesn't generate another key pair, but it signs the final challenge, the app ID and the counter, and spits out the counter and the signature itself. So this is a challenge response protocol run by the authenticator, sent back to the relying party. The server can verify everything and then knows, yes, indeed, this is John Doe authenticating. And the good news is, even if an attacker has been able to spoof or phish the password of John Doe, right, this authentication still protects against those scalable attacks, because John Doe still has his authenticator, so the attacker would have to get access to that authenticator and physically press a button. And this is something malware cannot emulate, right? Pressing the physical button, which needs to be done before the authenticator will sign anything or generate a fresh key pair. So this is how U2F works. And remember, the most important thing here is that the relying party already knows the user, because there is another factor which has been used before that, with typically username and password. Now let's go to the passwordless experience, the Universal Authentication Framework, UAF. And in this case, despite I've used a different way to illustrate that, it's pretty much the same technology, with the difference that the relying party doesn't know the user upfront. So for registration, obviously, you have to do the identity binding, so you have to know the user, or it's a completely new user, which is also fine. And instead of asking that user for a new username and please come up with a password stuff, I would just register, which means sending out a policy of the acceptable authenticators and sending out a random challenge, and then the FIDO client would process that, select the appropriate authenticator matching that policy, and that authenticator would verify the user, generate a new key pair, and generate the attestation object, including the public key, the authenticator name, the hash of the final challenge, very similarly defined as we have seen before, the name of the relying party called origin there, or app ID, and then sign that whole thing with the attestation in private key and send the attestation object over to the FIDO server, which will then store the public key after verifying the signature and checking the AAID against the policy. So then the authenticator has been registered to that new relying party, and the next time John Doe comes up at that relying party, there's no need for John Doe anymore to enter some username and a password. He could just swipe its finger, because the app would receive a policy, a random challenge from the relying party FIDO server, and the FIDO client would select the right authenticator, and that authenticator would verify the user, generate the signed data object after verifying the user and sign all the right information like the hashed final challenge, signature counter, the authenticator random, and so on, and sends the signature back to the FIDO server, which will verify that signature and check the authenticator model name against the policy that is indeed meets the requirements of that policy. And here you see the optional transaction text in some places, so you can use an extension of that authentication mechanism, which goes back to the transaction confirmation display, you might remember. So there are situations where to do a high value, for example, money transfer thing. Right? I want to transfer the $10,000 to John Doe. And in order to do so, my bank could send me a transaction text asking me to confirm I want to transfer $10,000 to John Doe. And so my authenticator, instead of my web browser, right, or my app, which might have a man in the app attack going on, my authenticator, which is a more smaller and more secure entity, would display the transaction text to me, and then I can, as a user, would be able to see, oh yes, do I really want to transfer the $10,000 to John Doe or account 12345? And then if I want to, I would swipe my finger, or if I don't want, I just abort, right, do nothing or press a cancel button. So in this case, the transaction text, obviously, or the hash of that gets included as well, so that the FIDO server can verify that what you see is what you sign, that the user has really signed what the server intended the user to sign, and the user has verified that whatever he wants to sign or whatever the authenticator displayed to him is what he wants to sign and accept it. And by letting the authenticator implement the transaction confirmation display, it's relatively secure and easier for authenticator vendors to implement, especially if you think of smartphones having technologies like TEEs, Trusted Execution Environments, supporting the global platform Trusted UI concept, in which the authenticator or the TEE essentially takes over control of the display and the touch input signal and let's say make sure that Android cannot and Android malware or applications cannot interfere with that, and only the TEE has control of that, and the user really sees what the user wants to sign, which is great if you remember old PKI days. So I started in PKI in '97. We were dreaming of such kind of things, and everyone was expecting people to buy expensive additional tools they could connect to their computers. And now we have the technology at our hands. And so it's very easy for the device manufacturer to use that Trusted UI technology for implementing authenticators. It might take some additional time to finally get there, but at least we have seen authenticators supporting transaction confirmation and authenticators being implemented in TEEs. So slowly but surely we are getting there. So in the beginning I mentioned that by separating the user verification from the authentication protocol, we also separate the parts which are relevant for the convenience, which is the user verification part, right? Everything the user sees, from the security relevant pieces, which are implementation technologies, the protocol which is hidden in the background, and so on. And by that separation, we are able to improve the security and the convenience at the same time. Now, if you look at existing technologies like passwords or passwords plus OTP, you typically see this kind of pattern here, right? Which means you have the convenience on the x-axis and the security on the y-axis, and it's either secure or it's convenient. And if you add more security, the convenience that gets degraded in some way, right? So you see it's like a curve, right? Starting at the top left and going down to the bottom right here. Now with FIDO, we can change that model, right? There is a right shift in the convenience based on using the same user verification method for all relying parties, for all servers, right? It gets more convenient. And then just by using FIDO principle, right? And then depending on the authenticator implementation, right? The specific user verification method used by that authenticator, there's a lot of scalability and competition of authenticator vendors when it comes to convenience, right? Is iris scan more convenient than a finger swipe or a PIN entry? And different users have different expectations on that. So there's room for competition for the market to decide and find the best solution, which is great. But FIDO, it's a right push and then opens up a scalability window of that. And in the same way, there's a push upwards in the security. Just by using FIDO, there is no secret anymore on the FIDO server, which is sufficient to spoof the user, right? And the FIDO, even if it's a PIN-based authenticator, it's not phishable, because if I enter the PIN outside the authenticator in some different window, for example, that different application can't do anything with that PIN because it doesn't have access to my private key first, and second, the authenticator doesn't allow anyone else, any software, to inject the PIN programmatically, right? It will always ask for a physical action, it being a finger swipe or PIN entry on a trusted UI, etc. So this makes a push upwards just by using FIDO. And then we have scalable security depending on the authenticator implementation, right? Whether it's using TE or running in the rich operating system or using a secure element. So just by using FIDO, we see we can get out of that trade-off pattern. It's either secure or it's convenient. We can have both and still have scalability there in terms of convenience and in terms of security. So I think I'm at the end of the core part. We still have enough time for questions and answers. So thank you very much for your audience, and I'm looking forward to lots of questions now.
Thanks, Ralph. This is Andrew again. So thanks everybody. We've had a whole bunch of questions come in through our questions chat box, and so I'm going to raise some of these, Ralph, and Ralph will answer them. We'll do our best to get to all your questions. For those we can't get to, we can send follow-up emails. So we have all your email addresses as well. So Ralph, let me start with one here. How does the authenticator authenticate to TPM?
Yeah, very interesting question. So from a formal perspective, it's not the authenticator authenticating to a TPM. The TPM needs to be an integral part of the authenticator. But again, it's a very good question because if you think of the internals of an authenticator, I mentioned there's a user verification piece in it, and maybe I can find that slide. The user verification piece, and there is the cryptographic engine. So if you think of these keys, the attestation key and the authentication key being protected by a TPM, there's still the need of having a user interface which performs the user verification, which has to somehow communicate with that cryptographic piece. And this communication channel is very relevant from a security perspective. And there are different approaches here. So the naive approach is to have some rich OS level software which asks the user for entering the PIN. The next best approach would be, now don't move that into the normal rich operating system, but make sure this is part of the kernel or an integral part of the security architecture of that operating system, so that malware, normal malware, cannot access that. You would need a root level exploit for doing that. So you could also do this. And the next thing would be you have, for example, a fingerprint sensor with its own cryptographic engine, which somehow has a secure channel to the TPM, and the TPM 2.0 allows a very flexible user authentication policy definition there. You could come up with a scheme where this fingerprint sensor, for example, would run some kind of channel response, could even be a symmetric key protected protocol between the fingerprint sensor and the TPM itself, and then only after running this secure, cryptographically secure protocol, the TPM would unlock the operation. So this generates a virtually secured or a virtual single authenticator, which is composed of two components. One is the fingerprint sensor with the cryptographic engine there, and the generic crypto engine in the TPM, which is more powerful, supporting the asymmetric cryptography. But you can compose that, which gives you one virtual boundary of that authenticator just by using this protection method. So very good question. There are different ways to approach that, and the most secure way is to have a secure channel and make sure that the user verification piece is not just protected by rich OS software or rich OS kernel, but by a smaller and more secure component. And there are, let's say, ways in modern chipsets or CPUs which support the implementation of that, and of course additionally fingerprint sensors, if they are more intelligent, they might come with their own chips and might contain cryptographic operations. Even if it's only the symmetric key operations, you could use that inside and run the standardized FIDO powered by the TPM outside.
Super, thank you, Rolf. Next question. Can we create a single authenticator that supports both key protection for TE or trusted execution environment and key protection for software?
Very good question. So yes, you can. The question is, how would that look like, and how would that be represented in metadata? So at this time, the FIDO model of an authenticator assumes that the user verification engines are somehow static. So you could use a PIN verification or a fingerprint verification. That's fine. It doesn't allow the FIDO server to understand whether you used one or the other at this time, right? You could discuss, try to come up with extensions to do those things, but at this time, this information, if it's implemented as a single authenticator, is hidden to the FIDO server. And this is part one. Part two is, now we don't only have different modalities supported, but there's different protection levels tied to these different modalities, right? Which makes it also very interesting from a security architecture perspective, right? An attestation key, what would that attestation key tell you? It's model X, and this model X is either the fingerprint in rich OS software, or it's the fingerprint in TE or TPM powered, think of it as being TE, and then or the pin-based thing in rich OS. So that could be both part of the description, but in the metadata, which is the other aspect of that, the metadata, the static nature is modeled today. And static means you have to describe the lowest effective protection method. And this would be, since the server doesn't know upfront, because there is no extension yet to convey the user verification method, which has been used dynamically back to the server. So the server doesn't know what kind of user verification method would be used for that key, and it would have to assume the weakest protection mechanism. So in the metadata, this authenticator would have to be represented today as key protection in rich OS software. But you can already do it. It's just, it's let's say, the representation might look a bit worse than it is in reality, because it needs to be the lowest security level just to be on the safe side.
Okay. Fantastic. Ralph, next question. If an authenticator is hacked and user authentication key was stolen, how can the relying party server in the back end be informed of the situation? And how can this be rectified?
Very good question again. So the question is, how would the user notice, right? There are ways to attack that, make the scenario a bit more concrete. Let's assume I have a rich OS software-based authenticator, and now I have malware on my system, and that malware somehow gets access to my keys. Maybe it's a smartphone, and obviously the keys typically are protected and isolated by the operating system on an app by app basis. Now assume that it's a root exploit on that mobile phone, and then the malware can just get access to the authenticators, which is another app's key in the end, if it's rich OS protected only. And then the malware would send that to some kind of attacker outside. Now, if the user doesn't notice that, the relying party doesn't notice that, that's bad, right? And you can't do anything about that. If the user notices that, the user could just deregister that authenticator from the relying party, which is the typical approach we are recommending. So once for example, I lose my authenticator, and this now gives an attacker the opportunity to run a physical attack to extract the keys, for example, right? In that case, I've lost my authenticator, which I notice, and then I go to my relying parties, maybe use a secondary authenticator. For example, I have one in my smartphone, I have another USB-based authenticator I plug into my PC, and then I use I've lost the pluggable authenticator USB token, but I still have my smartphone with me, so I can log in with my smartphone and say I want to deregister the USB token-based authenticator, or the other way around, right? So you can do those things. And this is what we expect to happen. If someone notices that the authenticator has been lost or compromised in some way, you can go to the relying party and deregister its keys.
Very good. Next question, Ralph. What happens if a user has multiple devices for the same network service? How is this managed?
So let's assume I have a tablet PC, a tablet with an app on it to access, I don't know, my service, and I have a smartphone, right? How's that managed? So from a formal perspective, I'm registering two different authenticators. One is the authenticator which is built into my smartphone, and the other is the authenticator which is built into my tablet, and the third one could be the external USB-based authenticator I'm plugging into my PC, for example. There are ways at this time outside of FIDO, but existing ways which can be built on top of the FIDO protocol, which would allow some kind of out-of-band binding between one authenticator. So you could use the authenticator on your smartphone to log in a session in an app on your tablet, for example, to do the identity binding and then register the authenticator on your tablet. So that's a way how you bootstrap and add this authenticator to that. It's the same with the PC and the browser-based application on your PC with the USB token authenticator. When it comes to deregistering the authenticator, it's the same, right? You log in with one of those authenticators you have registered, and then you deregister the authenticators you want to deregister. If you sell a device or you lost a device, you can safely use the other authenticator you still have and deregister the authenticator you have lost. So it's a good practice for a user to have more than a single authenticator and register more than a single authenticator to the relying party.
Super. Next question. Can an authenticator support TPM and TE at the same time?
The general answer is yes, and the question is how and what are the scenarios, and I can give some. And let me first, let's say, generalize TPM with secure element. So TE provides great protection against logical attacks. Secure elements provide great protection against physical attacks, but they do not include user interfaces. So what is best is a combination of both, right? So best security would be to have a TEE implementing all the user verification and the trusted the transaction confirmation display, the trusted UI piece of that, and have a secure communication channel to the secure element, which maintains the attestation key and the authentication keys. That would be the, let's say, the ideal way of implementing an authenticator. And now, whether you use a TPM or a secure element, is not a big difference. It's just a different term and different, let's say, form factor for that. The TEE, again, we are used to TEEs on smartphones primarily, but in the end, if you look at existing modern chipsets, for example, from Intel, they support concepts like SGX, which are can be used to create very similar security systems. So in the end, that would be a great combination to say, I have a secure user interface implemented in the TEE, and I've protected the keys in physical hardware as a secure element or the TPM. And I have a secure channel between both, right? As I described earlier, some kind of symmetric key or asymmetric key based cryptography between both elements, just to make sure that no malware is able to misuse the keys inside the secure element by emulating the authenticator as a user verification part of the authenticator running in the TE.
Okay. So briefly, we've had a few questions about the replay. I just want to remind everybody that we will be posting a replay. It takes us usually a day or so to turn this around. So the link to that will either be in your follow-up email on this webinar, or it's always available on the events section of our website. But we will be posting the replay and slides. Rolf, another question. If you're using only FIDO in lieu of username password authentication, what happens if the private key is lost by the client? For example, what if the Authenticator key store becomes corrupt?
Yeah, this is another good, let's say, reason to register multiple authenticators, right? And let's say my smartphone now has a bug or the display is completely broken, I can't use it anymore, right? Even though it might still remember my keys, they are in some way unusable. Those things might happen. And if I have registered a secondary authenticator, for example, the external USB token or my tablet, the authenticator embedded in my tablet, then it's easy for me to still log into the relying parties to my accounts on that using the apps and deregister that broken authenticator. And once I've fixed that thing, I can re-register that thing securely, right? If I don't have that, it gets us back to the account recovery scenario, right? So that's a piece where we need a solution, and it's a difficult thing, and we haven't found a silver bullet for that in that sense, right? So no solution which will satisfy all requirements we would have, first from security and second from privacy perspective, and would scale on a worldwide basis. There are always scenarios which break in some regions in the world, and so I think that's an area, perfect area to have competition in the market and competition for the best approach.
Very good. Next question, Ralph. Is U2F and UAF, are U2F and UAF both making use of metadata for the authenticator, or is it only for UAF?
I think if I look at the existing metadata service run by the FIDO Alliance, I think it's only UAF, but I know that we are in the way to add U2F support to that. And from a specification perspective, U2F support is already in. So there's nothing which precludes the use of the metadata service for U2F at this time from a spec perspective. And from an implementation perspective, I think it's a couple of weeks out that we get there.
Okay. Let's see. How does the authenticator authenticate to the TPM?
I think we had that question in the beginning. So the TPM needs to be an integral part of the authenticator. And the real question is, how does the user verification part of that authenticator authenticate to the crypto engine part of the authenticator? And you might, it's very important to get that securely implemented, and symmetric key protection would be sufficient. Let's say dedicated hardware wiring could be an approach on devices, right? Everything which protects against scalable attacks, at least, is a viable approach here.
Okay. Here's another one, a good question. How will FIDO approach crypto suites upgrade? For example, will U2F move to SHA-3, for example?
Yeah, so this,
yeah.
So if you, this is one area where we have slight differences in the different protocol families. There is crypto agility in U2F already. We have also crypto agility in let's say the next versions of FIDO, which are discussed in W3C and the FIDO lines. So I think that will be the most likely scenario. So once we get to and have to replace SHA-2 family with SHA-3 or get to different elliptic curves for whatever reason, in that case we need a protocol specification supporting crypto agility, which we have in the FIDO lines, but let's say it's not yet part in U2F. I don't know, it might be, we might get an update in U2F, or it maybe doesn't affect U2F anymore. We have to see once it's really concrete on the table.
Okay. Another question. I'm trying to sort through all these. Rolf, can you comment a little bit about browser support for FIDO?
Sure. If you look back at FIDO, that was really a very important point, and you see that different ways to approach that. The first thing is that we recognize that a lot of activity happens in the smartphone space, where the role of the web browser is different than the role of the web browser in the PC world. So we started with supporting the apps, and on the other hand we saw that Chrome has dedicated support for U2F, and we see Mozilla. So if you look into Bugzilla, there's a trouble ticket essentially open for adding U2F support to Mozilla. And so this might come. The question is, will it come for all web browsers? Potentially not. So in the FIDO Alliance we talked about that, and we finally decided to move the web API part of FIDO to the W3C. And that's what we have done some months ago, and now we have created a new working group, Web Authentication Working Group in the W3C, where we are discussing the Web Authentication Standard, which is essentially FIDO Web API, and it's just based on the observation that if a web browser vendor implements something, typically this something has to be standardized by W3C. Otherwise, it won't be implemented. It doesn't mean that everything standardized by W3C gets implemented in all web browsers, but if you want to get something implemented by web browsers, it needs to be in W3C. So that's what we have done. We are on a good track there. It's not yet finalized, but we have already published the first public working draft of that, which is published in the internet. So that's, everything is open. You can look into that. I think there's a lot of discussions, and I think the meeting minutes are also open to the internet, so you can look into our existing discussions on that. And there's an upcoming meeting, Web Authentication meeting, part of the TPAC in Lisbon. I think it's mid of September, where we continue that discussion and hope to come up and move it to the next level. So that's proceeding. So we expect that somewhere next year this gets really finalized, nailed down, and then will be implemented by various web browsers. And we hope that really all web browsers will support that web API, the Web Authentication API to use FIDO in web browsers. Until we get there, you can still use the out-of-band mechanisms I've mentioned before. So, for example, have a web application which asks for FIDO support in the web browser. If that FIDO support is not detected by JavaScript, you would just display a QR code which can be scanned by a passport application running on your mobile phone, having the FIDO Authenticator and FIDO support in it, and then the mobile phone would directly connect to the web server in a different setting, and authenticate essentially that session in the web browser. So that's at least a way you can use FIDO authentication even in conjunction with web browser-based applications.
Okay, great. So I think that's actually a great place to wrap up. These are fantastic questions. I could say we got to around maybe a third of them. So we'll do our best to answer these via follow-up. Rolf, thank you so much for your time today and for your insights, and thank all of you for attending. If you're still on the line, please do answer the survey before you log off, and stay tuned for a link to the replay and for future FIDO webinars. So thank you very much.